Example, for f of x equals x to the power of 1/3 on the closed interval from -8 to +8, f of -8 equals f of 8, and they both equal 2. But there is no c as in Rolle's theorem. Why is this not a contradiction? Let's examine what Rolle's theorem states. Rolle's theorem states, suppose that f is continuous on the closed interval from a to b and differentiable at all points of a to b open interval. If f of a equals f of b, then there exists some c in that open interval from a to b so that the derivative evaluated at that c equals 0. We do have a continuous function, f of x equals x to the 1/3. F evaluated at -8 is 2. F evaluated at 8 is 2. So why is there no c? Well, let's look at the derivative. F prime of x, bring the 1/3 down, x to the power of 1/3 minus 1 is -2/3. If I write this with no negative exponents, then I'd have f prime of x is equal to 1 divided by 3 and the cube root of x squared. Let's note that in order for us to have this derivative equal to 0, you have to be able to set the numerator equal to 0. However, this does not exist so that the derivative can equal 0. Let's be specific, on the interval from -8 to 8. Why is that? Well, let's look at the graph. This is f of x equals x to the 1/3 from -8 to +8. At the particular point where x equals 0, you have a vertical part of the graph. And if it's vertical, there is no derivative. Let's write that. At x equals 0, the function f of x is instantaneously vertical, and that means no derivative. Now let's go back and look at Rolle's theorem. It says on a to b, it has to be differentiable at all points, but at x equals 0, f of x is not differentiable. So since it doesn't meet the hypothesis of Rolle's theorem, there's no requirement that it meets the conclusion, and that is why there is no contradiction here.